We'll start out by thanking Shripad for the invitation to give this talk. This actually occurred from some conversations we had on Twitter. And since this meetup is online, I can guarantee that this talk will be 100% COVID-19 free. However, I do hope to infect you with some different ideas about data. So other than that, I've tried very hard not to be too provocative, but I think I've failed. So we'll just have to proceed with the slides I have and see where it takes us. As a lot of you probably know, my university background is in theoretical physics, not computer science and not data science, so-called, or statistics for that matter, although I've dabbled in all those things. But it's worthwhile knowing my background because physics is an empirical science. And a lot of physicists, I think, have forgotten that fact. They think it's all math. And as physics undergrad, we're spending maybe about 30 or 40% of our entire time in the laboratory doing measurements of some kind. So the whole idea of data acquisition and statistical analysis sort of becomes almost second nature after a while, after you do enough of it. And typically, by contrast, in the computer science degree, you don't do that kind of thing. So it doesn't make any sense, really. So when I was putting this talk together later today, I was thinking when I was doing undergraduate physics labs in Melbourne, I was at a rather new university and they had a very different approach. So where you would normally have done a physics experiment, say, trying to understand the period of a pendulum and how that period is independent of the mass of the pendulum and all this sort of thing. In the old days, you would have actually set up a pendulum and measured it with a stopwatch and all that kind of thing. But the labs that I did were completely different, actually incredibly modern when I look back on it. I'm not sure I fully appreciated it as an undergrad, but now it is that the labs were entirely electronic. So instead of setting up a real pendulum and measuring it with a stopwatch, we actually simulated the pendulum with an LRC circuit. So first of all, you set up the circuit to model the physical system you were going to try to measure. And then you also used electronic instrumentation to do the measurements. There was no stopwatches. It was all done with electronic timers and so on. So looking back on it, it's quite incredible that we did that, and that the physics department was so far-sighted because, of course, all modern physics is based on electronics as far as experimental observations are concerned. So I think that colors my thinking a lot, and that's probably the basis on which I'm going to try to explain things with regard to the title of this particular talk. So just so you have that in mind. So I think some of the things I say may be unusual to you because I'm coming at it from that physics-based perspective. So here's some of the things that I've said about data in the past, particularly on Twitter. Obviously, the title of data is wrong. I'll stand by that to the death. Treating data as divine is a sin. Measurement is much more than just sucking data up from various repositories. And you can't trust the data scientists with data because they don't understand anything much about measurements. And one important thing to keep in mind about measurements is that it's a process, it's not numbers. Numbers are the end result. What I'm going to be talking about here in this presentation is more about how the numbers get sourced. Now, generally I'm doing performance analysis, but quite a few of the examples I have put together here don't come from performance analysis, or at least not computer performance analysis. So, but as we're passing through, I just thought I'd sort of just put another non-provocative slide up about top output that you might see in Linux, for example. And so what I'm on about is, this column of numbers, for example, here, these are all wrong in some sense, some value of wrong, which is what of course I'm going to explain. I'm just picking on them because they look like those numbers have high precision because they have a decimal point in them. Whereas these numbers over here, which have to do with memory pages and so on and so forth, they're not the same thing because they don't have a decimal point. That doesn't mean they're any more believable, but they do look different. So these, the CPU measurements, percent CPU busy, look somehow more believable because they have a decimal point, but that's actually not true. So what the top data does show us is at least two different kinds of data. One is continuous data. It's like the CPU column I was just referring to, or the timestamps, for example. Those numbers have fractional values, and that's the reason the decimal point is there. They're real numbers, and they include 0 also, obviously. Nothing may be happening on the CPU. And they're presented as decimal values because they're fractions, typically, of some kind. The other possibility is the discrete data was on the right-hand side of the top output. They're represented by whole numbers, which also includes 0, positive integers, basically. And those numbers represent things like memory pages or the number of packets in and out of the system and so on. Now, there's other kinds of data which statisticians talk about, such as categorical data, nominal data, and ordinal data, and so on, which I'm not going to get into here. We don't really need to take that into consideration for what I want to talk about. So before we get too highfalutin about data and measurement process and so on, let's just go right back to basics. And when I think basics, I think something like this. I have a plank, a wooden plank, and I need to cut it to a certain length. And you know the old adage, measure twice, cut once. So here's somebody with their ruler out and a pencil. They're marking a line on the plank where they want to make the cut with a saw. And that's the first step. So they've measured it carefully, presumably. And then they go ahead and make the cut. And there you see the cut that's been made and the line, the original line. You see that towards the bottom of that, the cut is much closer than at the top for some reason. And the point here is that, of course, there is no such thing as a perfect measurement. And the closer you look at the cut that's been made by the saw, the more ghastly it looks, because the original line, that's to say the pencil line that was originally marked on the plank, is the statement of intent of the length that was needed. But when you make the cut with the saw, of course, there's all sorts of compounding issues come into play, such as which side of the width of the saw blade are we talking about? Are we going to cut down the middle? Do we cut to one side? Do we cut on the outside? Do we cut on the inside? The saw blade has a certain width of its own. It has saw teeth. The saw teeth tears through the wood and, of course, doesn't make a perfect edge by any means. And so, you know, rather than having a perfect measurement, we end up with shaggy endings. Just typical. But the point remains that there's a difference between the intent represented by the pencil line and the result, which is the actual saw cut. So we could call that the actual value and the measured value. So the expected value and the actual value are never identical. This is just a ground truth. So the question really is, well, how much slack should we allow in between the expected value and the actual value? And if we look at construction, for example, wood frame for buildings has a tolerance of about 1/8 of an inch around the original pencil line. In the USA, it's about 2 millimeters on the ISO standard in the EU. So, you know, the point is that there is something called a tolerance. That's to say some amount of slack between the pencil line that you drew and the actual cut that you made can be off either way to about 1/8 of an inch, something along those lines. Now, that seems kind of self-evident, and you may even be familiar with that if you do any kind of building or DIY of your own. But we could ask the same question. For example, it's tax season here in the United States. So with regard to income tax, how accurate are the amounts on your income tax filing? You probably never even thought of that question. But the same process is involved. There's an expected value and there's the actual value. And those two things may not be the same. In my case, I have an accountant who does all that for me. I feed him some numbers, but then he does his thing. And I have no idea whether that's accurate or not, because he's just taken my numbers. Sometimes he makes an adjustment. I know in one year, he was taking the wrong amount for the deduction that I can make on my the interest payment on my mortgage. You can deduct that in the United States. But he'd used the wrong deduction for several years. So there is an example where the expected is not equal to the actual. So I don't know whether the IRS picked that up and hit me with a penalty or not, I don't remember. But the point is, he made a mistake. I didn't make the mistake, he did. And he's the CPA. On the other hand, when I see the tax forms, which are about 2 inches thick in the United States, when I see his result that he's going to submit to the IRS, there's no indication anywhere in those documents of any kind of error, such as the one I just described. There's no place to put such an error. In the case of the global financial crisis, 2008, how many mortgages went into default? Nobody really knows. How much real money was actually lost? Nobody really knows. But these are banks. That's their business. How could they not know? So the point is that in case of construction, there are what's called building codes, which have things like tolerances and so on. In the IT world, we generally don't have any such building codes. There might be some things that come close to that, but it's not a general thing. So more generally, all these things are done kind of ad hoc, on an ad hoc design basis, and there's no real awareness of what was expected and what's actually happening, maybe until it's too late or until the separation between the expected value and the actual value becomes so big, you just can't ignore it anymore. The idea of having an initial tolerance is usually not there because nobody knows what it is because they don't know how to do measurements. So let me drill this home even more by showing you some bad data examples, which have not to do with IT. They do come from physics because I happen to know about them. So, and they're quite alarming in their own right. So one of them has to do with some experimental measurements that were done by an Italian team of physicists that were running an experiment called OPERA, which measured some properties of neutrinos. Neutrinos are a particle that's well known now, and it's neutral, it has no charge, so actually it doesn't interact with matter very much. It does, but it's a very, very weak interaction because there's no electric force involved at all because it's neutral. So the neutrinos were being generated at the Large Hadron Collider in Geneva in Switzerland, where the Higgs boson was eventually detected and so on. And then those neutrinos are fed down to this experiment, which was being done just outside Rome in Italy. And anyway, the major point is that after some years of collecting data of this type, they noticed that in certain circumstances, the velocity of these neutrinos coming from Geneva, the LHC in Geneva, according to all of their measurements, must have been traveling faster than the velocity of light, which in physics is denoted by the letter C. And that's a problem because that implies that Einstein's special theory of relativity, for example, is broken if that's true. So these experiments that were being done in Italy, by the way, are extremely difficult measurements to make, very, very difficult measurements to make. And nonetheless, if you have data that does indeed show that neutrinos are traveling faster than the velocity of light, then something is wrong somewhere. And that's a pretty big statement. So it's a big deal because even Einstein said it only takes one experiment to prove me wrong. So he was fully aware of that himself, by the way. So data check. So now they do analysis of the data because they know that if they're going to go public with an announcement that these neutrinos are traveling faster than the velocity of light, that's going to be a big deal. You better have your ducks lined up. So they do the data analysis. This is the sort of thing that data analysts do all the time, or data scientists, I guess is the trendy term these days. And at the end of their paper, which I read, by the way, they conclude that the data is accurate to what's called a 6 sigma confidence level. I'm not going to talk about confidence intervals tonight. But 6 sigma confidence interval, just to have an idea of what that means that according to the data analysis, 6 sigma means there's a 1 in a billion chance that those data are a fluke. So that's a pretty strong statement. The normal requirement for particle physics, by the way, is only 5 sigma, which is equal to about 1 in a million chance that it's a fluke. And that's in fact the criteria that was used for the Higgs boson, for example, which was announced, I think, in 2012 or so. This was around about the same time, 2011. So here we are, a very surprising result. If it's true, Einstein's special theory of relativity is in big trouble. You do the data, or they did the data analysis. They have 6 sigma confidence level in their data analysis. And here's what happened. Within a few months, within a couple of months, the team withdrew the paper. They published it. They spent about 6 months arguing with each other about whether they should go ahead and publish this thing. But once they had the data analysis done at the 6 sigma level, they decided to go ahead. Now, I don't know what happened in the interim between September and December, but they withdrew the paper. And I did find out why. And here's a picture of the problem. So what you're looking at here is, this is the backside of what's called CAMAC instrumentation. These are the recorders that are recording things like times and other data electrically, just in the way that we did when I was an undergraduate, actually. And so this is the instrumentation that's actually measuring the data. And the arrow is pointing down here, and I'll blow that up for you so you can see what's going on. So around about the time they published the paper, this optical fiber cable which feeds into this instrument, or connects to this instrument, the data comes from here, the signals come from this instrument, was unlocked. The cable has to be locked onto that socket there. And the person who is responsible for this, and that's their only one job, is to set this instrumentation up correctly, had apparently overlooked this. But after they published the paper, it was discovered. And when that optical fiber cable was locked onto the instrument, the superluminal velocities disappeared. In other words, 6 sigma confidence level was 6 sigma confidence on garbage in is garbage out. And the team manager ultimately disappeared also. As far as I know, I saw in the news that he got fired. I'm not sure it was actually, I suppose being the team leader, that makes sense, but I actually myself, I can't understand how somebody could not find this, because, you know, even I know there are 2 major things that can destroy your measurements. One is cold solder joints. That's to say where the wires are electrically connected and soldered into, say, a PC board, for example, or a mechanical connector, of which this is. Those 2 things alone, any physicist worth their salt knows that, or anybody who uses any kind of electrical instrumentation should know that. So I can't understand why the person who was just responsible for putting this equipment together didn't see that. That just doesn't make any sense to me. But anyway, that's what happened. So you can have all of the data science in the world, which can give you 6 sigma type of confidence level, and is absolutely meaningless. That's why this is a good example. And the place where they're getting screwed is in the source of the data. That's to say the measurement process. This is the equivalent of doing the saw cut. This is where the numbers come from. So it's the data source you have to pay attention to. This is the data receiving end. You know, this is way downstream from the actual creation of the data. So you can look at the data to kingdom come, but if it's garbage, this really doesn't make any sense. Although it looks pretty good on paper. And if you had a statistician look at that, they would sign up for it and they would say, yes, that is a correct analysis, which I'm sure they did do. But it doesn't tell you about this. All right, next example, also from physics, but completely different kind of example, completely different kind of physics. And this is Hubble, Edwin Hubble, 1929. This, I claim, is the most important scatter plot in history. And what we're looking at here is Hubble's plot that he published in his paper in 1929. And I'll just try to explain the axes to you here. So if you haven't seen this before, this is the velocity of these data points, and these data points represent stars. And so what Hubble is doing, Hubble and other astronomers are collecting data and measuring the distance to the star. That's on the x-axis, and it's measured in this funny unit that astronomers use called a parsec. 1 parsec is equal to about 3 light years. Just, you might be more familiar with that. Light year is the distance light travels in 1 year. So these are enormous distances, and these are megaparsecs. This is millions of parsecs, so 3 times a million light years. So these are enormous distances, and that's why there's not a huge number of data points, but there is quite a lot. So the x-axis is the distance to that star, to the whichever dot you're looking at, and then you look across on the y-axis, and there they're measuring the velocity with which the star appears to be moving relative to the other stars, and also including us on the Earth. It's called the recession velocity. And what Hubble is doing is he's plotting the velocity, that's the recession velocity on the y-axis, the distance to each star on the x-axis, and he's then done simple linear regression, which every statistician knows how to do. And I know that Hubble did do this. He's not a statistician, but he figured out how to do it. And what he's saying is, on this basis, there's a relationship, even though the data is scattered about that line, the relationship is linear. And of course, you can have statistical indicators to tell you how good that model fits the data. The data is actually good. So with that, you conclude that the further out that you look and you see a star that's further away from you, the faster it will be traveling away from you and all the other stars. So there's a linear relationship between the velocity with which the stars are moving and their distance from the point of observation, which is here on the Earth. That was that's what we're trying to establish with these data. Now, the idea that it's a linear relationship like this is quite fantastic, because what it means is that if he then takes the linear regression model, as a statistician would, you'd notice he's also forcing it to go through the origin there. There's the origin. So we could have gone through the y-axis anywhere. There's 2 parameters. There's the slope and there's the intercept on the y-axis, but you can clamp it to go through the origin because that makes physical sense. And if we do that, then there's only one possibility now, and that's to measure the gradient of that line, which regression will do for you. There's the regressor, and there's the regressand, or the response variable, the y-hat that's being estimated. So the y-hat is in kilometers per second. X1 is the distance, the enormous distance to the stars. By the way, they weren't all stars. Some of these were galaxies actually, but that was unclear at the time in 1929. So they were just called stars back then. Now, if we take the slope of that line, that's to say the rise over the run, that will give us a rate. And that rate is the expansion rate of the stars, because they're all moving away from one another. You can imagine them as being like on the surface of a balloon, and the balloon is blowing up. And that rate at which the balloon is expanding is what this model is describing. So it says, if we take the slope, we can figure out the rate at which the balloon is expanding. That's the expansion rate. And of course, this is the first real empirical evidence that there was such a thing as the Big Bang, although that wasn't completely clear at the time in 1929. That's what Hubble was pushing, the idea that this data and this scatter plot and this linear regression analysis supported the idea that the universe in some sense was expanding, and that probably was due to a Big Bang. Now, if we take that slope, which of course is also now known as the Hubble constant, that rate, expansion rate is a Hubble constant. Since it's a rate, it's inverse time units. So if we take that number and tip it upside down, then instead of talking about a rate, we're talking about a time, the inverted slope. That time is the time for which the universe has been expanding. Pretty cool. So, of course, Edwin Hubble double-checked all this, and he even found that maybe he had to take some other factors into account, which I won't go into here, and he corrected the slope slightly beyond the original regression, and came up with a number which, instead of being 423, was something like 465. So there's the new Hubble constant. You invert that number and you can tell the age of the universe since the expansion began. And that number corresponds to 2 billion years, which is rather interesting because there's a slight problem. The slight problem is that it was already known, even in Hubble's time in 1929, the Earth was something greater than 3 billion years old. Today, we know the number is more accurately from radio dating and so forth, and that is 4.5 billion years. But in Hubble's time in 1929, it was only known to be bigger than 3 billion. So now we have a problem. The Earth is older than the universe, which can't happen. So Hubble, of course, would have known this. So I like this scenario because this is, if you do this kind of analysis, if you're doing statistical regression on your data, no matter what it is, and it's not going to be as exciting as this data, but whatever you're doing, you are going to be faced with the same problem that Hubble was faced with, and that is, what am I going to do? Because according to this analysis, Hubble was fully aware of this tendency. This says this can't happen. Physics says it can't happen. You can't have the Earth before you have the universe. So the Earth can't possibly be older than the universe. That just can't happen. So therefore, the data says you're wrong. So toss it. You know, nice idea, but it doesn't hold up. The physics is against you. Or you publish and possibly destroy your career, or at least give a bad talk and get a lot of flack. So this problem everybody who does data analysis is faced with, you know, not to this extent, obviously, but in a smaller degree. You have to really think about, what am I going to do? Because the data looks like it says one thing, and yet it really seems like there's some good evidence that maybe the universe is expanding. So maybe it really has something going for it. And now you have to decide, are you going to tell the world or not? Most people would put it in the circular file, I would say. Hubble was a bit more arrogant than that, so he decided to go ahead and publish it. And by the way, if you look at his paper, he only mentions the expansion of the universe in the very last sentence, if I remember correctly. So he really plays it down. But of course, everything else that he talks about, including this analysis, this linear regression analysis of all these observations, is screaming expansion of the universe. He knew that, so he just downplayed it at the end. He said, you know, this may have something to do with understanding, you know, the possible expansion of the universe, which has been theorized by theoretical physicists, including Einstein, not including Einstein, but people who read Einstein's work. Einstein actually was unaware of this and didn't believe it, actually. So what happened is this. If we look at the situation today, I'm skipping ahead, 2003 is the last data that I've seen. I don't keep up with this stuff that closely, but the last data that I could find conveniently was from 2003. And this just gives you an idea of how this has continued since 1929. Now in this plot, we've got the same thing. We've got distance to the stars, because there's many more stars now, and they're much further away than what Hubble was looking at. In fact, Hubble's data is down in this little red square down here in the lower left-hand corner near the origin. So this is vastly greater distances are being observed, these stars, and nonetheless, when you look at their velocities, which we can measure very accurately using spectrometer, by the way, I won't go into all that, but these are very accurate measurements, you can see that if we do the correction, because remember Hubble messed it up, he did the correction the wrong way, but if we recorrect for Hubble's mistake there, the idea that there's a linear relationship between distance and velocity, which is the main point of Hubble's paper, is correct, because that linear relationship still holds up today. Now the slope of the line has changed. It's 70, it's not 400 and something, it's 70 because we corrected it completely. But nonetheless, the point is Hubble took the chance and published. And by the way, when the paper first came out, he got a lot of static from lots of astronomers saying that this was kind of rubbish and this was hardly good evidence and blah, blah, blah. What actually happened was, in the next decade, so I guess the 1930s, the quality of the optics in telescopes, these are all optical telescopes back then, the optics improved dramatically year after year after year. And so what happened is that Hubble's problem was that his data is bad, the model is correct. So this goes back to my statement that data comes from the devil, only models come from God. And so if you have religious fervor about the model, i.e. that the universe is expanding, and you have the fervor to believe that this evidence is supporting it, even though it's a bit shaky, and it's not right, but there's something going on, and that the data is not sufficiently accurate. If it was more accurate, then this problem would go away, which is probably what Hubble was hoping for. And therefore he published, and he placed his bet in the correct way, and he's actually the winner. And not only that, he now has the orbital telescope named after him. So, as I said earlier, everybody who does this kind of analysis is faced with these kind of issues very often, not such a dramatic way, but nonetheless, you have to question, is it the data or is it the model? And in my experience, I generally put my money on the model. I have to understand the model. If I think I understand the model well enough, I will usually vote for the model. So maybe that's a physics thing, I don't know. Because I'm fully aware of where, these kind of problems. By the way, in looking at this plot, you'll notice that it has these funny horizontal lines here. So these dots are the actual position of the star, the distance of the star. And then there's a horizontal line there, which I'll explain a bit later on what that means. Notice there's no vertical line here. All right, so now you may be saying, oh, that's all well and good because, you're talking about measurements that are this continuous data type, according to statisticians' terminology. That's to say, numbers that are represented by decimal points, decimal fractions. But there are other kinds of data, which I mentioned, such as discrete data, which is essentially, cardinals, counting numbers. So if you're just counting things, well, that's kind of easy, isn't it? I mean, here's an example. This is a paper from 1935 written by Einstein and two of his colleagues at Advanced Institute in Princeton. And this, in fact, is the paper that kicked off the whole thing about entanglement, which has now become like the major attribute of quantum effects today. So if I just look at the discrete number of authors of this paper, it's clearly just easy to count them. 1, 2, 3. There's no questions about accuracy or measurement there. So if you're just counting things, isn't that just a simple case, and you wouldn't have this kind of a problem in that situation, would you? Well, let's look. So here's another CERN collaboration, Large Hadron Collider again. And this is a paper published in 2010, and that's about a decade ago. And notice that the authors here are not counted because they're called the Atlas collaboration, which of course is just a proxy for the entire experimental team. But that team is so big, you couldn't list all the authors in the place where you normally put the author names, as you would have done in 1935. There's too many. So that raises a question, well, how many authors are there in this team? So it turns out, of course, they have to get the credit just like Einstein did in 1935. So their names have to be published somewhere and in connection with this paper. And so here's what it looks like. The author list is 15 pages long, appended to the actual article, which has a page limit of 4 pages. So there's 4 times as many pages or so listing the authors as there is the actual content of the paper. And it turns out they're listed in this way, and there's more than 3,000 people. So you may say, well, gosh, that's a lot. But how do I know what the actual number is? I'm saying there's about 3,000. There's actually a bit more than 3,000. Now, how would we figure that out? Now, of course, you may say, well, easy, just write a program and it'll count it for you, which is a good idea, except that it's not necessarily so easy because there can be sources of error. For example, you have to, if you're going to put it into, say, something like R, you really want to convert it to flat text, so ASCII. So you have to take these names. Notice the names have separated by commas, but they also have these funny numbers as little exponents here. That refers to their institution, their affiliation. And some of them have multiple affiliations, an A and a B, blah, blah, blah. So this gets a bit messy. So your program has to parse all of that stuff correctly and figure out where the new lines are and all that sort of thing. So it has to take all this weirdness into account, and probably two different people writing two different programs are going to get two different numbers. And then there's other issues about, like, did we include everybody? Should we include the tea lady? Because she, you know, if she didn't serve tea, then people wouldn't have been doing their work. So do we include them or not? Well, of course, that's never mentioned. And we have the same kind of problem with streaming counts, sources of error. The counters are sensors of some kind. Are they working correctly? Remember the problem with the opera team in Italy. Is the event being triggered correctly? Is the count number being transported reliably, or does it get interfered with and come out as another number at the end? Is it being accumulated correctly? And, you know, what about the statistics, quantiles, and all the rest of it? So there's plenty of places where things can go wrong, just like cutting a piece of wood, even although we're now talking about discrete numbers or cardinals or counts, counting things. So even if you're doing counting, once the counts become big enough, you end up also with problems and sources of error that you really need to try and check for and decide what you're going to do about it. Now, I think this is my last example. Yeah, this is my last example. This does come from IT, which is load average, which is a metric that's used a lot by sysadmins and people doing capacity planning and so on and so forth. And by the way, just for your information, there's the load average numbers there. Notice there are 3 of them. People who use Linux and so on will have seen this a million times if you issue the uptime command or so on. This, by the way, is the original performance metric. This is the first performance metric put into any kind of operating system or computer system around about 1965. So what's that, 55 years ago or so? And what it does is, what it's measuring here, that notice these are continuous numbers. So these are decimal fractions of some kind. It measures the run queue length, just so you know what it does. But it's measured in a slightly weird way. So it's not your average kind of average. It's not just taking an arithmetic average or something like that, because of course the queue length is fluctuating. So it tries to take those fluctuations into account, and it has a very clever way of doing that, I must say, which I discuss in my classes, but I won't go into here. But another way of looking at it, if you're an electrical engineer, it's a low pass filter. So what that means is that any spikes in the data, which a statistician would call an outlier, are basically filtered out unless they remain persistent. If they remain persistent, then they do get included. And there's a clever way of doing that that doesn't take much. It's only a few lines of code, but the idea behind it is actually very interesting. So nonetheless, this, as it sits in Linux today, was originally implemented in 1965, and although the code implementation is different, the implementation itself, the way it works, is identical. So this is, of course, written in C in Linux, and I don't know what it was back in 1965. Certainly not C. So nonetheless, the actual calculation is the identical calculation in both cases. Now, that's interesting and good to know. I haven't explained why there's 3 numbers. We won't go into all that here. But here's a more important thing for our talk today, and that is in Solaris 2.0 and Solaris 2.2, in the kernel where the load average is calculated, as it is also in Linux, that code was modified. More importantly, Sun never told anybody about it, and I think I'm not necessarily blaming Sun management per se, because I don't think they were told about it by the person or people who changed the code in the kernel. I'm not 100% sure about that, but probably they didn't. But ultimately what happened is Solaris got released, and now the load average is behaving differently from the way it behaved previously. And it remained broken until Solaris 2.3. So if you're a sysadmin or a capacity planner using that load average number, for example, this particular one, the 1 minute load average, if you're using that to do system administration activities or capacity planning analysis for future server sizes and so on and so forth, suddenly all this changed underneath you. and you wouldn't have known because you wouldn't have been told about it, but suddenly all your numbers or your models would have run into trouble or said or predicted something completely different from what they were predicting before. And you may or may not have noticed that. So good luck. So this is a real problem because it means because the software is so malleable, and any software engineer can make this change because they think they're doing a good thing. You know, the road to hell is paved with good intentions. So they may even think they're doing a good thing. By the way, I've seen this in many different guises, which I won't come to here. This is not the only case where I've seen this. Trust you don't know about it. And the only one can know about it is you have to do a regression test on your vendor performance, including links, because that's the way you would possibly changed and how much it's changed, therefore know how dramatic it is in terms of how it's going to impact how you've been using those numbers in the past. So not only are we talking here about, you know, cutting some slack to do with tolerance, this is the whole thing's just changed underneath you. It's in software. It's easily done because it's malleable. Nobody was told about it, including you. And now you're wondering what the hell's going on if you happen to notice. Otherwise, all your projections could be wrong and you might think they're okay. This is a serious problem. Nobody talks about this stuff for some reason. So let me come more to the point now. What am I talking about here? So back to the title, all data has errors. So all data is wrong in the sense of, going back to the wood cutting example, I put down my pencil line, that's my expected value, that's my statement of intent. Then I run the saw along that line in some way or other, and that becomes the cut, which is the actual value, independently of what I expected. And there's going to be a difference. There's always a difference between those two things, particularly when you're cutting wood. That's pretty obvious. And that's why the building industry has certain tolerances for that, because if it's outside that tolerance, then you have to do it again. And the point is that any kind of, that's the basis of all measurement processes like that, like cutting a piece of wood, because you have an expected value and you have an actual value. And there's always going to be a difference. And all measurement instruments, whether it's a ruler or whatever, an instrument or an electrical instrumentation, electronic instrumentation, like the opera example, is doing exactly the same thing. It might look more fancy, but it's the same process. So all measuring introduces wrongness. By wrongness, I mean errors. That's why I can say all data is wrong, because all data is coming from a measurement process one way or another. Something had to source the numbers. And that comes from some kind of a process which you may or may not understand. So ultimately, the real question is not that. It's the question of how big is this wrongness and can you tolerate it? Because even though you find out what the error is, if the error is acceptable, such as 1/8 of an inch in the building industry, then you're okay. But at least you know what it is. If it is outside that tolerance, then it's not okay. And this is the basis of things like service level agreements, or at least it should be, not necessarily how it's done, but it's how it should be done. So you really need to understand the source of the errors and how big they are, what is their magnitude. And the problem I have here, and the reason, the basis, the motivation for this talk is that this aspect of generating data to me seems to be, you know, a case of out of sight, out of mind, that we have a problem where people doing a data analysis really have no idea about the measurement process itself. And because they're blissfully unaware of that measurement aspect, the whole notion of errors never even enters their head. And actually, Shripat and I were just talking about before we came online. And so I relate that example also because it's also rather interesting now that I think about it. Of course, you're fully aware of this pandemic that we're having. And on Twitter, there's a guy who, data analyst, I guess he is, or a data scientist, whatever, who works for the Financial Times. And he's gotten a lot of visibility in the last few weeks for generating plots of the curve, you know, you've heard of this about flattening a curve and so on and so forth. This is the SIR model plots of the data, and the idea is to try to flatten that curve so that you don't soak up all the capacity in all the hospitals with people who have respiratory failure due to the SARS-CoV-2 virus. So that's become a massive interest now. And of course, in California and also in India, you're worrying about where you are relative to the peak in that SIR curve. So that's what everybody's interested in. So this guy's generating these plots every day. And he does it worldwide. He does it for all the countries where he has the data. And he even breaks it down in some cases by state. So he has California and Florida plotted, and New York, of course, and so on and so forth. And you can see all these curves. They're plotted together in various ways in many different dimensions, but he breaks them all down. And you can choose the plot that you like to look at. And what's interesting to me in the context of this talk that I'm giving here is that this guy falls into this category. He's blissfully unaware of how these data are created. So I know that because when he plots his data, there's no indication of the error in those data. All he does is take the data point, he gets from WHO or CDC or where all these lots of different data repositories that he's using, all of which are completely credible. I don't have any problem with that. As I said back to this talk, you already know that the Chinese government and the Russian government and others have been accused of monkeying with the data, or possibly not even measuring it correctly. There's all sorts of issues there that we do know about. Therefore, just like cutting a piece of wood, there must be errors in those data. There has to be. But the guy from the Financial Times never indicates that, because I'm quite sure he doesn't know. He must be, somehow aware of what I've just said, but he never has it in his mind when he's doing the plots, because if he did, he would immediately resort to showing the amount of error in those data. And there's a way to do that, which I'll show you shortly, but he doesn't do it. So I claim he's blissfully unaware, otherwise he would do it. So I think there's another interesting example of where, it looks great. It's look great, they're readable, and you can see where the curves are and how you're approaching the peak. So for example, Wuhan in China, they're well past the peak, they're well into the tail, and now they're starting to open up Wuhan city and so on gradually and monitoring the data and so on and so forth. So everybody else is now trying to catch up to that situation, actually. So, what he's doing is quite useful and no problem there. But I'm just pointing out that there's no signification of the amount of error in that data. And there is error there. And that's my beef. There's always error, but people don't show it. So therefore they think the data is pristine, and it's not. All right, this brings me to how to express the error. Well, there's many different ways you can do this, but I'll just show you one very simple example. And if you could do this with your measurements, this would be a fantastic improvement. So it's not that difficult. Nothing you have done it before, it wouldn't be something that would come to your mind, because there's a procedure for it. So I'll show you what it is without going too deeply into it. So the first point is you can't have a single data point, because you can't estimate error from a single data point. You have to have multiple samples in order to do the statistics correctly. So we need n data points, whatever n is, something bigger than 1. Next step is we take the sample mean. That's the, the arithmetic average, basically. And then on top of that, we need to take the standard deviation. And what I'm talking about here is the standard deviation of the data, not the sigma and mu of the normal curve or something like that. Those are theoretical parameters. I'm not talking about that. I'm talking about the data. So I'm talking about the sample mean and the sample standard deviation, which is, by the way, the standard deviation about the mean. So I've got to have the mean first before I can calculate the standard deviation. So I'll come back to that later, possibly, why this is so important. This is much more important than any kind of percentiles and all that sort of thing, by the way, and you can ask me about that later on if you want to. So then we take the standard deviation and we calculate something called the standard error. That is just simply the standard deviation divided by the number of samples and take the square root of that number. So it's the square root of the number of samples, and we divide the standard deviation by that number. So that defines the standard error. And then we write the result of those n data that have been measured as the mean value, which we just calculated, plus or minus the standard error, which is the standard deviation over square root of n. And now you see I have a mean value, that's to say an average value of those n data. That's pretty intuitive what that means. But on top of that, now I have a range where that mean could sit. And that's the way I quantify the error margin, the amount of slack that I have in my measurement process. So I just report this result of these samples as the mean value plus or minus the standard error. And the rule of thumb is, or a rule of thumb is that sometimes people like to talk about the percentage of the error. So a rule of thumb is that a standard error, a relative standard error of about 5% is typical and acceptable in many cases. So for example, if we did the analysis on the top data that I showed you earlier in one of the early slides in the talk, I would expect that to fall within plus or minus 5% range. If it didn't, I would be very worried. I'm going to assume it probably does. But I would like to see somebody who's actually done that checking. It sure isn't minus 12 volts. Now, here's some code. I'm doing this in R just to show you how simple this is. So I've just generated some fake data here. Just to make the point. So this is coming from a normal distribution with a mean of 10, set at 10, and a standard deviation of 3. I'm doing that for a reason, because then I'm going to do the analysis that I showed you and I'll see, does that actually stack up against these data that I generated by calling this random variates from R. So if I plot those data as is this, the time for in milliseconds, anything else, I'll call it in seconds, they look like this. So there's a typical kind of a bar plot or histogram type plot. So on the x-axis, I have the number of the sample, and on the y-axis, I have the time, which is the random variable that I generated here. And you see the thing fluctuates. Every different measurement has a different result. So every time I cut the piece of wood, I get a slightly different result. I mean, that I drew originally. So if I now take the mean of those numbers, I get a number 9.87 and so, and its standard deviation is 3.23. I create the standard error in the way that I just described, and I can print it out, and here it is. So I would report these data samples, these measurement values, as 9.87 plus or minus 0.32 milliseconds, as an example. And in fact, if I plot those the mean and the standard error on the same data, it looks like this. The horizontal line is the mean at 9.87, and the dashed lines above and below are the standard error plus or minus 0.3. So now I have the number, which is the average of those measurements, all these measurements that were made, plus or minus a range of values which this value could take. It could be bigger than that value, that's the mean, be slightly smaller by an amount of up to 0.32. So the point is, I can see, I could take that as a percentage and so on and so forth. I can see how big is that error relative to that number. Of course, if people don't do this kind of analysis, all you see is a number like 9.87. You don't know where that came from. You don't know how much error is in that data. When I represent it this way and I report it this way, you can see the amount of error. And now you can make judgments about, is that acceptable or not? It may or may not be, depends on the context. Now, there's other ways of representing error. And of course, I go back to physics because they use this stuff all the time. And the other technique is, it's the same analysis, but instead of representing numerically, which is perfectly fine, by the way, you can also include them on the data. And you see, this is just I just picked this because it happens to be the original data set that came from one of the experiments at the Large Hadron Collider, once again from the Atlas team. And there's the bump in the data that it corresponds to the Higgs boson from 2012. But more importantly, for our purpose, you can see that the black dots here, these are the data, and you can see they have these little vertical lines attached to them. And that, in fact, is the standard error of each of those data points. And primarily, you can see the vertical line. That's represented vertical line. So that's the standard error in the number of events per giga electron volt. You know, whatever all that means, doesn't much matter. But that's the vertical line represents what's called the error bar for the y-axis, whatever those units happen to be. And in fact, if you look very closely, you can see there's not actually points there. There's a slightly squished point, which is actually a horizontal line going through the data point, but it's not very wide. And that's the corresponding error bar for the x-axis. That's to say the mass in GeV, in giga electron volts. So the mass is about 122, 4, 6, about 126 is in fact the mass of the Higgs boson. So you can see immediately from this that there's more error in the energy, in the event count per energy range than there is in the mass estimate, because I can see the vertical error bar is much bigger than the horizontal error bar. But that's very, very useful, because I can see where the biggest errors are coming from. They're coming from the this measurement, not from the mass itself. The mass itself is quite accurate, relatively speaking. Let me just go back to the Higgs data, the Hubble data, and explain these horizontal lines. Just now you know what these mean. These are the error bars, same thing. It's the standard error around each of those data points, which is the mean value. That dot represents the mean value of all the measurements of that particular star, whatever it happened to be. And that horizontal line is the representation of plus or minus the standard error at that distance, at that average distance. Now, what's interesting about this, what hits you immediately here, or at least hits me, is that we've got quite significant horizontal error bar. That's to say, bigger error in the distance measurement, relatively speaking. And that error gets bigger and bigger and bigger as we go further and further out, because it becomes more and more uncertain as to those distances. On the other hand, there's no vertical error bar, or nothing observable. If there is one there, it's inside the dot, so it really doesn't count for much. And this says that the velocity measurement, on the other hand, is extremely accurate. And I don't want to take a lot of time, but I just explain to you why that is. Just think about this for a moment. This makes perfect sense when you think about it. When you're looking at the stars at night, you're looking along a line of sight, which is a radial, you're looking radially at the star from the Earth. And of course, just looking at the stars in the night sky, you have no idea about their distance. In fact, the way you see the stars is very much the way the ancient Greeks saw them, which was as though they were all the same distance on a kind of a black velvet type of a dome, and they're all just embedded in this dome at the same distance. Well, of course, we now know that's not true. Hubble, amongst others, proved that's not true. But now comes the issue of, well, how do you measure the distance of the star? Because you're looking along the line of sight. How do you measure that distance? Well, you have to do some very, very clever tricks, and I'm not going into the details of that, but basically you do it based on their brightness in a very special way. And you have to have some standard stars, if you like, where you know the physics of those stars pretty well, or you think you do. And then you compare the brightness of other stars that are different from those stars, and the brightness gives you the measure of the distance. Now, you can guess from what I'm saying is that there's lots of room for error in that kind of a measurement or that kind of an analysis. Nonetheless, that's what's done. And if the stars are relatively close to us, it's pretty good. As you go further out, of course, the error gets greater and greater and greater, even although we've changed the reference from the time of Hubble, where Hubble even, by the way, back in Hubble's time, just so you understand, in 1929, it wasn't even believed by most people that the universe was bigger than the Milky Way, which is now the Milky Way is just our own local galaxy, which sounds almost laughable when you think about it, because everybody knows that's not true now. But back in 1929, most astronomers even believed that the universe was basically the Milky Way, and that's all. One of Hubble's observations showed that that star, which turned out to be another galaxy, was actually outside the Milky Way, which is already a hint that something's not quite right back in 1929. But that was all very, very murky, just like the age of the Earth being 3 billion years old. That was also murky. Now, so I can see from this error indication, these horizontal error bars, immediately that the biggest problem is the distance measurement. So that's the most unreliable. But the velocity measurement seems to be incredibly accurate. Now, how the hell can that be? If the distance is so difficult to get a handle on, why is the velocity so easy? And here's the trick. So you take the light from the star and you pass it through a spectrometer, prism basically, and you split the light. And all stars basically burn hydrogen. So the hydrogen on the Earth is the same as the hydrogen on the star, no matter where it is in the universe. And when you take the light of the hydrogen, it forms a spectrum as the Balmer lines and so on and so forth. So we know exactly what the hydrogen signature from the hydrogen atoms looks like here on Earth. It's a discrete spectrum, atomic spectrum. And when we look at the starlight from these different stars, we see, in fact, it's exactly the same spectrum for hydrogen, but it's shifted. And it's shifted because of something called the Doppler effect. Because they're moving away from us, the pitch of the light is dropped towards the pitch, going more towards the purple end if they were coming towards us, or it goes towards the red end as they're going away. It's called the red shift. And because we're looking at discrete spectrum, and that's in the nanometer range, it's so accurate, there's no error bars because it's an incredibly accurate measurement. Whereas the distance measurement is relatively very poor, actually, even though we've improved the technique enormously in the last few decades. So these error bars are another way of showing error, which incredibly means. And of course, if you want to know the numbers, you can go and look up the data and you can find the exact error bar and so on. But this would be a very interesting way of showing these things visually, even for IT data. But of course, you don't see that normally. Another approach, which I'm not going to this evening, is with confidence intervals, which I'm sure you've heard about. And we already mentioned a 6 sigma confidence level. Well, in particle physics in general, it's 5 sigma, so one in a million chance that it's a fluke. But just to show you, here are the 1 sigma and 2 sigma confidence bands in green and yellow around the data, which is from another experiment called CMS, which is also looking for the Higgs. And there it is. There's the bump. You can see that bump lies outside the confidence range because it is indeed the Higgs boson at 126 GeV. So there's the evidence, because you see it lies outside that confidence band. It's in the 5 sigma range, which is not shown here. But nonetheless, you can see visually, even though the confidence interval calculation is a little bit different, it's related, but it's a little bit different from the standard error calculation. You can see immediately and visually that, in fact, these data are very meaningful because they lie outside the confidence interval in this particular context. Or you might be looking for data that lies in the confidence interval, which would be these data. And you can see they wander around the dotted line in each increment of the x-axis or y-axis is the mean value. So there's the mean, and then there's a spread about the mean, which is measured by the sigma value, that's to say the standard deviation, just like I was explaining before. Now, another problem, which I'm not going to get into, is, of course, how many digits do I report? So I skipped over that here. I've shown, 2 digits right-hand side. Is that really appropriate for this measurement? Well, I have to understand something about how the measurement is done in order to figure out that. I'm not doing this evening, it's too complicated. But this is called the number of significant digits. And basically, the main message I want you to take away is first significant way a bit of understanding what's the appropriate number of significant digits. And the main point is that you can't have more digits reported than your measurement instrument is capable of producing. So you can't get accuracy out of the vacuum, so to speak. So I explain all that in chapter 3 of my book, but I just wanted to make you aware of that. I skipped over that point here. I'm just showing 2 decimal. I don't even know if that's correct because this is just a fake example, but I would also have to consider whether the 2 decimal places are actually meaningful or not. They may or may not be, or I might be able to have more. So, for example, it's very typical now that you can do microsecond type of measurements on the CPU and so on. So most of that stuff is bogus because things are never really that accurate as far as the process level stuff is concerned. So reporting, 6 or 8 digits out to the right is actually meaningless, but they're put there because that's what the data has in it. And so people just keep them there. They don't know how to do these significant digit assessment, but it has to be done. All right, so the other thing is, which I'm going to wrap up on, is accuracy versus precision. So basically, if we look at Hubble, Hubble didn't have a precision problem. Hubble had an accuracy problem. He couldn't even get on target, really, because the actual value of the Hubble constant that we now know is about 70, and he ended up with a value closer to 500. So forget precision. He didn't even have the accuracy. But the reason for that is not because he's an idiot, it's because his data was very poor by today's standards. So he had systematic errors in all of his observations, and was also true for the other people, other astronomers making observations, which he also used in his scatter plot. And I'm fairly certain, I mean, can't point to it any particular statement, but I'm pretty certain Hubble would have been aware of that that's a likely problem area, and probably, I'm sure he would have thought about that and thought hard about that before he decided to publish his paper. And of course, he tried to correct it, but he went the wrong way for reasons I won't go into. So it wasn't a silly mistake. It was everything that he did was completely reasonable given the poor state of the data at the time. But despite all that, as you saw, his linear model, his conclusion, his overall conclusion survived because, of course, models come from God. So I also discuss accuracy and precision in my book. You have to worry about both those things. Roughly speaking, you know, the accuracy is how close is the mean to the actual value. That if we're assuming normal distribution of errors, for example, that would be the mean value of the normal distribution, and the precision, as you've already seen, is contained in the sigma value, which is the measure of the spread around that mean, the standard error and so forth. So these are all things to be aware of when you're reporting errors. So it's a real career on its own, in a sense. You can see it's quite detailed. So another main point is that, you know, only the paranoid survive. So you have to check your results, you have to check, and then you have to check again. As you saw with the opera in Rome, they did all that and they still got it wrong. They went public, and then for whatever reason, the culprit, that's to say the bad connector on the instrumentation, was finally discovered. So you just can never be too careful. In the abstract, I mentioned something about waterboarding your data. Well, I don't have it, you know, we don't have time to get into all of that, but just to give you an idea, just so that I can leave you with something to think about. So I actually have an example that I do in my classes where we look at some load testing data or performance testing data, where they measure the throughput and the response time, because any load testing tool like LoadRunner or JMeter or whatever, that's all standard stuff. So that generates that data for you, basically. And you, of course, you can plot it. We won't get into the fact that, you know, quite often these are just single data points, which is not cool, because I can't really represent the error if you're only going to give me an n of equal to 1. So I really need more data, because everybody has an excuse. We don't have time to measure more than one load point, but whatever. This is the throughput curve. It's concave, so there's the offered load in terms of the number of client generating requests into the SUT, the system under test, and there's the throughput, transactions per second, whatever. It's a concave function, so I think that's believable from a performance analysis point of view. But let's look at the response time curve. The response time curve also is concave. Now, I know from queuing theory that can't happen. Every response time has to be convex. That's to say, it has to be going up that way, like a hockey stick shape, classic hockey stick. But this data isn't. And the point here is that in the class, I show you quite a lot of different examples of this kind of effect. And all of the people doing the load testing are completely clueless that this is wrong. They just report this like that's a good thing. Now, what this means, of course, is that as I increase the load, the response time remained constant. So if you actually have a product that works like that, my suggestion to you is ship it, because it will never get any better than that. From a performance analysis point of view, this is broken. There, the hockey stick handle, if that was a hockey stick handle, is suddenly snapped. And the question is why? What's going on? So once you realize this is not correct, you then have to start digging in to find out why it's not. So this is what I meant by waterboarding your data. It's not just a question of collecting the data and worrying about the measurement process and showing error, which we can't do easily in this case, but that's what we should do ideally. More than that, I need to explain what is going on here so I can fix it up so that it measures the thing correctly. Now, one way of going about it in this case is that since I have the throughput measurements, the data, and the response time data, so I have two sets of data. I know this is incorrect, but I'll just go with it for the moment because that's what's being reported by the load testing tool. I then apply Little's law. Little's law tells me that if I take the product data, response time data plot, forget about whether it looks right or not, just take the product of those two numbers. That I will call N. N is the actual load on the system. That's to say the number of active processes in the system. And now what you can see is that as I increase the number of client threads on the driver's side of the system, the load testing system, I would expect the actual number of threads to equal the offered load, the offered number of threads from the driver's side. So it should go up along a straight line like this, inclined at some angle. But in fact, what we find is when we do the Little's law analysis, in fact, you see that N flattens out just like it does here. Because what's happened, in fact, is that the actual load on the SUT is being throttled on the driver's side. For example, you might fire up 200 threads, 200 active users, but if your thread pool was limited to 150 or 120, let's say, something like here, for whatever reason, then even though you're increasing the number of scripts that are running, they're not actually running because there's only 150 threads to handle them at any one time. So the offered load is the number of scripts that you're firing up, but the actual number of threads that are running is whatever threads can support it. And if it stops at 150, because that's the total number of active threads in the thread pool, then it's going to plateau out. And that causes this response time to have this flattened curve also. So the fix, it turns out, one of the reasons this example is interesting, because most people think there's a problem on the SUT, that's to say, the database or the application or the multi-tier system that represents the real application. Of course, that's usually where the problems are. But by using Little's law against this data, I can extract under duress the truth about what this data is trying to tell me, which is to say that I'm thread limited on the driver side of the system, not on the SUT side. Okay, so, summary. So the title said all data is wrong. I hope you can understand why I'm saying that now, because a measurement is a process. That process introduces errors, a systematic error, random error, and so on and so forth, which we can go into in great detail, but not tonight. And we need to see the error margin to decide what's acceptable, such as the Hubble data and so on. And measurements are represented by numbers, but that doesn't make it math. It's got nothing to do with math. These are numeric representations of that measurement process that I've given you some examples of tonight. I hope that you can understand that. And just because I see a number like 72.37 means nothing, because I have to see the error that's associated with that number to decide whether that's acceptable or not. How wrong is it? If it's not very wrong, then maybe I accept it. Also, don't exceed the number of significant digits or significant figures in the expression. You can't have more digits in your reported value than was produced in the measurement process. And then I need to go through this simple procedure, which you can set up as a program to report something like the standard error, which I've now explained to you. So, but even then, reporting errors in this way doesn't guarantee that everything is meaningful. After all, the opera guys measuring neutrinos, they did this kind of analysis and they convinced themselves that it was accurate to the 6 sigma level, but it was 6 sigma of garbage. Okay, if you want to know more about this kind of thing, there are several chapters in my Gorilla book on this, and I also, of course, have online training classes called Gorilla Data Analytics, where I discuss this and many, many other topics in data analysis, particularly for IT applications mostly, everything from linear regression to machine learning. If you let me know. And the questions and comments if there are any. So thank you for your attention so far. Hope you're all still there.
Yep. Thanks, Dr. Gunther. Any questions? Maybe you can take it now.
I'm not seeing anything. So do I have to look somewhere to see them, or what? Or do you want to read them out to me? What's the best way? Because I might need to refer to my slides, so I'm going to keep the slides up here.
Can unmute themselves and ask the question. I see on chat Vinay has a question. Vinay, you should be able to unmute and ask. Hey, thanks for the talk. So I have a simple question. So what are your
Thank you.
thoughts? What are your thoughts about research reproducibility and evaluation in peer-reviewed publications? Is this concept prevalent in physics conferences also?
Sorry, can you speak a bit more slowly? It's very hard for me to follow exactly everything you're saying. Can you
Yeah.
say? There's some words I'm not getting quite.
Right.
Sorry,
I think
just repeat more slowly. Just say it more slowly.
right. So, what are your thoughts about research reproducibility and evaluation? So, there's a lot of a lot of systems conferences lately do artifact evaluations, and we evaluate measurements of every paper to make sure that the measurements are, the artifacts are functional. The paper is in itself is claiming is the data is there to to support its claim. So is this prevalent
Yeah.
in these conferences? Does this, what's your thought about research reproducibility and validating these measurements in general in peer reviewed conferences, I mean?
Well, yes, it wasn't just the rate at which you were speaking. Actually, I don't know anything about that subject at all. If I understand, I'm not familiar with that at all. So I guess you're saying, see if I can paraphrase. You're saying that well, you're talking about conferences. So I guess there are conferences where they discuss
Okay, so
when you're reviewing papers and so on, you see certain values expressed and so on, so to support the argument of the paper, and you want to, and then at the conference they're discussing techniques to apply to see whether those values that are being expressed are even credible, and so any way of verifying. Is that what you mean? Is that what you mean? Oh,
yeah,
okay. Well, yeah, okay. That's interesting. I honestly don't know.
Let me elaborate. Let me elaborate a little bit. So this is
Sure.
this is kind of a new practice. So usually this came from a very programming languages conferences kind of background, but nowadays conferences that are systems and conferences of machine learning conferences are also starting to follow this, where basically when papers are accepted to be published, so there will be a committee which works with the authors and independently validates their data by
Okay.
and then making sure that the measurements that they have are the same measurements that we see when we do independent evaluations. So I thought this was also sort of prevalent.
Right. Yeah.
I thought this was prevalent in physics conferences too, but looks like it's not. So.
No, well, no. I think okay. So I do understand better now what you're saying. I mean, I'm not an expert in that area at all, but I see what you're asking me, and it's an interesting subject from the way you're describing it. So I think I do see what you're saying, Stan. One of the things that's different today from even maybe 10 or 15 years ago, and correct me if I'm wrong here, but what I've seen is it's now generally the case that there's an expectation that when particularly for a very empirical paper, whether it's a medical community or whatever it happens to be, where they're, as you said so succinctly, that they're supporting their argument, their conclusions based on, measurements they've done of whatever, I think you called an artifact, or whatever that context happens to be. The one thing that's different, I believe, check me if I'm wrong on this, is that there's an expectation now where it's often found in what's called supplemental materials in the big peer-reviewed journals, where in principle, it's possible to go and get your hands on the data that the authors claim they used in their paper. Do you agree with that statement?
Yeah, that's right. So
so therefore, okay, so that's one. See, that didn't used to be the case. There was no way of doing that even online and so on. But today, with the internet and all the rest of it, that has finally come to pass. And so I guess you could say that anybody reviewing that paper, whether it's for peer review or after the fact, even after it's published, then in principle, I can answer your question. In principle, then, if you can get your hands on the data, I would say, I haven't done this personally, I can think of, you could imagine once you get a little bit experienced in doing it, for example, what I would do, here's how I would do it. I would be looking at a certain paper, let's say, maybe it's in medical community or something, I would be expert in, but not that, but let's just take medical example. I sometimes do that too, by the way, some interesting papers. You look at it. What I do quite often, first of all, I start from the end of the paper, not the beginning. And I try to work backwards to see if I can figure out how they got to their conclusion before they tell me in the paper. That's actually a fair bit of hard work, but sometimes I do that. And the reason I do that is because in that way, it's very easy, or it becomes easier. It's harder work, but on the other hand, it's easier to spot discrepancies that way because they stand out more. Whereas if you start at the beginning of the paper, you're already becoming imbued with the notions that the author wants you to become imbued with. Whereas if you start at the end, he didn't expect that. So if you see what I'm saying. Now that's one thing. So I mean, I do apply this kind of thing in various guises. Sometimes as an alternative, I will go to a certain section of a paper. Like, for example, I don't know, last year, I think somebody sent me a paper that they were going to have published and asked me for some comments. Now, it turned out that I didn't understand all the elaborate algorithms they were talking about, something on distributed systems, interesting enough. But what I did see, they actually did some queuing models of their system. And so I immediately glommed onto that as, well, I'm supposed to understand something about that. So let me check that out, because if I see problems there, then quite likely there could be problems elsewhere. And so what I did was I went through the analysis of just that section, and I found, I had questions. I mean, things I didn't really understand why they did what they did. And so it wasn't so much to do with numerical data. It was more to do with the logic of the argument based on that section. And so because it was somebody I sort of vaguely knew, it wasn't a showstopper, but I provided that information back to them as feedback. Now, if it could have also included more numerical information that was not provided in the way that I just described a second ago. So there was no online data I could go and look at. That there could have been, but there wasn't in that particular case. But in addition, if I had already suspected that there was something wrong with the way the queuing models were being done, or even if it wasn't wrong, it's like, well, why are you doing that? Why didn't you do this other way? That would have been more useful, or something like that. If there was also numerical issues, I could then, in principle, go and look at that part of the numerical data. And then, to answer your question, finally, I would start doing the sort of thing I'm doing here. I would, for example, take the easy route. I would plot some of the data, and then I would, if they didn't have any expression for the errors in their data, which quite often they don't, I would then try to, figure out what that might look like and try to plot it. Could I try to plot error bars or something like that? If you see what I'm saying. I would explore these different as like cheap shots that I could do, because I'm not going to take half my life.
Right.
Looking for easiest route, as they say, and I'd be aiming for something like, this makes sense. Does this match what they're saying in the paper? And then numerically, I would try to plot that. Visually, does it even look right? Or is there something in the visual that I don't really understand? I thought I did, but I don't. They need to explain that, this kind of stuff. Do you see what I'm saying? And this forms a kind of critique, over and above what you might do if you did that.
Right. Cool.
Because I do the homework. I mean, I have, you know, too many years of experience. So I know what I'm looking for. I know what kind of technique, for example, Little's law or some statistical analysis or linear regression. I know what to throw at it in order to bring to the surface what I think is the problem or the inconsistency. And then once, if I do that, if you put something out on Twitter and I don't agree with it, you're going to hear about it.
Oh, cool.
So similar thing, I think, right?
Yeah.
Yeah. So yeah, I think all of these techniques and many others are applicable. And I would, once again, I'd be looking for the cheap shots. You know, I wouldn't be spending a whole lot. I'm going to spend my career just working out this guy's paper. I'm going to look for the straightforward things where I think the real problems are, the most obvious inconsistencies, and check them out. And or you know, sometimes it's not so brutal. It's like, well, if I take your data and I apply the USL to it or whatever, or some queuing model, whatever, it looks like this. What do you think about that? That doesn't seem to completely agree with what you're saying, but maybe it's something else, another aspect that you're. What do you think about? I'll ask them, what do you think about that? So, you know, it can go that way too. Just exploring in more depth what they're saying on Twitter or wherever.
Okay.
So yeah, good question. I didn't really think about that before.
Anybody else?
What? Only one question? You're kidding me.
Yeah, I have a
Go ahead.
Yeah, so my question is regarding completeness of data. So like all of these examples that you're showing me are typically related to physics and
yeah.
As
Just because I happen to know them and they represent
yeah,
really interesting situations that it's very hard to find them elsewhere. Anyway, yeah, sorry.
Yeah, so as you were going through the examples, what was coming through my mind was, you know, real world examples in terms of how data being generated when interactions are going on with humans, not, you know, instruments that are generating those data, right? So what are things to watch out for when, for example, like one basic example that comes to my mind is like, you know, polls in an election or something like that. So when you're collecting data where there's a human bias, there's a very, very strong tendency of, you know, data being inaccurate at the very, very source it's being produced. What do you do about that? And the second question is, you know, let's say you have a set of data and let's say you have reasonably accurate what the data points you have, but maybe you don't have complete set of it, or, you know, what even is completeness in terms of when you start talking about, okay, this, I have enough data to start doing some analysis on it, or maybe I don't have enough data points to. So this is like a very ambiguous line for me, or in terms of like, you know, maybe it's problem context specific, maybe it's not. So what do you think about that?
Yeah, well, these are all very good questions. Not easy to answer either, but they're kind of outside the scope of what I was talking about here, but they are related, of course. But so, I mean, there's several things came to my mind while you're asking that question. So I guess, so one thing, which I didn't discuss tonight, but there's a way of answering that last question that you asked is like, you say, how many, another way of expressing what you were talking about is how many data points should I have for a given measurement in order to believe that I have credible statistics when I do the actual analysis, right? That's sort of a similar thing to what you're asking me. You call it completeness of the data. Well, one way of thinking about completeness of data is, do I have enough data, or is my sample small? If you have a very small sample, then even from a statistics point of view, it's not going to be very representative of the overall population that you're trying to represent statistically. So if we look at it, if I just rephrase it that way as a statistician would say it, that you can answer questions like that. You can figure out how big your N sample points, in the number of sample points, how big that value should be in order to satisfy certain criteria for generating meaningful statistics. Like I said, but it's a procedure that's too complicated to go into, but it's based on the confidence interval. So you take the notion of confidence interval, which is basically formulated around the Gaussian or normal distribution. Confidence interval is very similar to the standard error, but it's slightly modified by the z-score and all that stuff, but I won't go into all that. So you take the z value and multiply it. That puts a bias. So one way of thinking about this, I was thinking about this earlier today if somebody asked me this question, so I'm asking it myself. When you use the standard error, as you saw in the physics data that I showed you, both for Hubble and for the Higgs boson and so on, you can see that the data point, the mean value is always in the middle of that error bar. However, if you use confidence intervals, there's a bias that comes in from the normal distribution, and typically the data point won't necessarily sit in the middle of that confidence interval, which is a little bit different from the standard error. It's related, but it's a little bit different. So that's one way of thinking about this. Confidence interval is a little bit more sophisticated in that sense. And you can, anyway, the point is, once you figure out how to do the confidence intervals, you can use that same machinery, turn it on its head, and how big of an N would I need in order to meet that confidence interval criterion, if you see what I'm saying. So there's a way of answering your question about, is my data complete? I don't know that data is ever complete, but I can certainly ask, do I have enough sample points in order to have credible statistics? And the answer is yes, you can do that. You can calculate how N should be for a given criteria. It's based on confidence intervals. It's not intuitive. It's a bit messy, but you know, if you're going to do it all the time, you just script it up and just push the button. But yes, you can do that. When going back to your other example, we were talking about polling, where you know there are humans that are, in a sense, the instrumentation doing the data collection, let alone whatever's being written on the survey or the census or whatever it happens to be by the you know, the address. So people poll, so on and so forth, because you know this always has error in it, and we saw this just a few months ago in Iowa when they were, you had a new app that basically broke and messed things up in terms of getting the data back to the central collection point, and so it was a total disaster, and it was much more error prone than if it had been done by humans doing door-to-door surveys or polling. And but nonetheless, even if a human's doing it, yes, there's going to be errors. And I mean, you know, what you do is you take the history. One way of doing it would be to take the history of such polling events, you know, different elections and so on and so forth. And from those data samples, you could figure out what is the standard error, just to keep it simple and based on what we were talking about tonight. You could figure out the standard error for that stuff. So you could, in fact, figure out the degree of error in those polling data in terms of an average and a standard error based on previous polling, because you would look at, you know, what was polled versus, you know, what the outcome of the election was, or something like that. And we've seen that many times, including you know, even the election of Donald Trump. Back so it was 2016. All the polling suggested he was going to lose. So, you know, that's a massive error. And of course, there's been a lot of discussion about that ever since. So, you know, what is it, 538 or whatever? I forget the exact name now. I follow it on, which one is it?
530, I think Nate Silver is the guy who runs it.
Yeah, well, that's the guy I was trying to think of. Yes, I follow him on Twitter and so on, and he's the people who work with him. And so, yeah, I mean, he had egg on his face after that too. So there's obviously polling error there. And so, you know, the polling didn't capture the mail-in votes and all the rest of it. So, but this is fertile ground for statisticians, of which Nate Silver, I don't know if he's actually a formal statistician, but he plays around with numbers like that. So he did baseball before that, I think. But anyway, yeah, so there's definitely a way of getting a handle on these things. But I guess what I'm saying tonight is that that's an important area that is often overlooked. And, you know, I'm more than happy for somebody to just go back and calculate standard error. By the way, so I think that, I hope that answers your question. Is that okay, what I'm saying?
Yeah, makes sense. Thanks.
Okay, now, but now you've reminded me of something else. So I've been going on tonight about, you know, putting in the mean and the plus or minus the standard error. That's a very straightforward way, and it gives quite an intuitive expression for the amount of error in the data. So if you can do something like that, you know, I'd be over the moon. That's great. But just going back to the top example for a minute, there is still a problem, and I'm not quite sure what to do about this. So where you have something like top, where part of the exercise is to sort of pack in as many metrics as you can, which is, you know, also a bit over the top, if I can use that expression. But you know, where you have these numbers, for example, there's so many numbers in here, it would be difficult, or I could accept that it's difficult to put in, you know, the error bar, the error margins would take up, you know, yet another column for every type of metric that you want to report, including even here for memory pages and so on and so forth. So, you know, this becomes a bit messy. Now, what I could accept, given you know, modern computer technology and everything, I could accept that the numbers get reported like this. I mean, I'm actually, you now know what I mean when I say there's a wrong. They're wrong in the sense that they don't give me any indication of error, and they're actually a bit misleading, because here I see one decimal place reported. That's like one significant digit on the right-hand side of the decimal place. But over here, I see two significant digits. What's up with that? So the point is, I can see inconsistency here already, but I could accept the output as long as there was an additional capability provided to me such that I could say, click on a certain value and drill down into its underlying error and so on and so forth. So although the error is very important, it doesn't necessarily have to be reported in situ every time, because that might be rather difficult. But the main thing is, as long as the tool, whatever it is, provides me with a way to drill down to find out more information, including the level of error in those data, I'd be okay with that, in the sense that it's not reported immediately, but I can click on it and drill down to get the context if I want it. That would be an acceptable compromise, I think. So, you know, I've been banging on about standard error, but it can be difficult to report all that stuff without taking up a lot of space. On the other hand, I don't really believe humans can really absorb all of this information. Usually they're looking for one thing or two things. They're not looking for all of this necessarily. So, you know, I'm not sure that this is in the best representation when it's all said and done. And if you remove some of the filters you don't want, there would be space to put the standard error in. But either way, as long as I can get my hands on it one way or another, I'm cool. By the way, that takes me back to that point about the guy doing the COVID-19 spreading and the SIR curve in the Financial Times. Remember I mentioned him earlier? And I said to you, I know that he doesn't really understand what he's doing, because he just shows data points and he doesn't show any error bar. He could do, but he doesn't. That's the reason I made that comment. And that's just typical of so-called data scientists. You know, lots of work put into how to visually display the data, but no indication of the amount of error in those data, of which we know there's a significant amount. So just reminded me of that, so thank you.
Dr. Gunther, I have one more question.
Okay.
So how, I mean, so first of all, most of these things assume that instrument is correct in terms of reading. So how do you, what is the role of calibration in all of this? How do you calibrate the source of measurement itself? I mean, do you care about that when you read?
Oh, well, of course, yes. I mean, well, you usually, well, I mean, it depends on the actual context, but as far as electronic instrumentation is concerned, usually when you buy it from a manufacturer, it comes with its tolerance range included in the data sheet or whatever, the manual or something like that. So the manufacturer will calibrate that equipment. Now, you may not accept that level. You may want higher tolerance, and if that instrument is capable of higher degree of accuracy, which it may or may not be, you may want to calibrate it for yourself. So basically what that means is, put in simple terms, all you're doing, see, all of these are comparisons. Even when I do the pencil line on the piece of 4x2 and I cut it with a saw, I'm doing a comparison between my ruler edge and where I draw the line, and then I make the cut. But the ruler line is the measurement, or sorry, the expected value, I should say, and then I make the shortcut, and then I'm comparing. That's the error that I was talking about. But we could also talk about the straightness of the straight edge, and so on and so forth. So I mean, after a while, even a metal ruler, you know, like I was showing here, can get banged up, you know, and may not be as good as it was when you first bought it. So the point is that all of these things, the actual measurement itself and the measurement of the measurement instruments or instrumentation or tools, are all forms of comparison. So if you want to recalibrate an instrument for yourself, because you may think it's drifted, for example, drifted out of the original tolerance range that as it came from manufacturer, that can also happen, then you have to have another instrument of the same type, which is within tolerance, which you can check, and you then compare that instrument that you believe is working correctly within the correct tolerance range. You compare the instrument you think is now drifted out or has a problem, or you want to increase its accuracy, whatever, with that instrument. So that's how it's done. I mean, the point is, the one thing that's common to all of this is that it's all about comparison. You're comparing expected with actual, no matter what. And that can include even the measurement instrument itself.
Okay.
So it's the same kind of procedure, really, when it's all said and done.
Sure.
Yeah.
So when you come to TPC or TPGH benchmark, do they give this sort of calibration just to make sure that, you know,
Oh,
so that would be what it is, right?
That's a good question. Boy, that's a good question. Yes, and yes, and sort of yes. Actually, you asked about TPC, but I'm just thinking about spec, which is similar. It's for CPU and well, everything that's not database these days. Actually, let me, if you allow me, let me talk about spec, because I know a little bit more about that. I forget exactly what TPC does. They do like, for example, in TPC, you know, it depends which benchmark you're talking about. For TPC-C, for example, it's only certain transactions that complete in less than 2 seconds or something like that can be counted. No others can be counted. So they have these kinds of criteria, if you will. Now, in the case of spec, I know a little bit more about that. So, for example, the spec number, if you go on the spec.org website, the numbers that you see reported there are the result of multiple runs. So the good news is that, you know, they do require multiple runs of the benchmark codes. And then the number that they end up using is the geometric mean of those values. So you've got to, so there's several things going on. Got to do multiple runs, so that means n is bigger than 1. That's a good thing. I think they require 3. It's not fantastic, but it's better than 1. You then have a comparison between whatever your machine, your CPU is doing versus their reference CPU, which I forget now what that is. It might be an IBM Power or something, I can't remember. But you then compare the time on your CPU relative to the time on their reference CPU, which they chose. And then you take that ratio of your time to their time. And then the third thing you do is, there's like, I don't know what it is these days, but roughly 10 benchmarks a piece for integer evaluation and floating point evaluation. But for either of those, you take all of the 10 numbers that you get as elapsed times relative to their reference machine, and then you take the geometric mean of those numbers, and that gives you your spec number that would be reported on their website, for example, if that's what you were doing. So, so a little bit, I'm trying to be unusually diplomatic here. You know, I have to give them brownie points for trying. I'm not suggesting that that they've really done a great job of that, but at least they've done something. And you know, we can quibble about whether it should be the geometric mean and all that stuff, but the basic ideas are correct. The idea of multiple runs are correct. Having a reference machine is, you know, it's okay. It's a weak spot because the trouble is the reference machine changes, you know, after about 10 years or something like that. So that means it makes it difficult to compare what was going on now with what was going on 20 years ago. And sometimes when you're doing capacity planning, you really might want to do that, if not for performance sake, maybe for cost sake or something like that. So there can be plenty of reasons for wanting to do that. Or whether you're still on Moore's law or this kind of thing. So there's plenty of motivations for doing that. Changing the reference every so often is really annoying, but you know, understandable as a practical matter. And of course, there are ways of overcoming it because you can always find the appropriate fudge factor between the different reference machines. So it's not a showstopper. And they don't get into a lot of statistical analysis. I don't think they even report the standard error in the way that I've been talking about it. They could do, because they have the number of runs at least to do something like that. And so you could do, and in any event, whether they do or not, you could take the data and do something like that plausibly. Do you see what I'm saying? So sometimes it's not done, but there's enough information there, or you can go and bang on their door and say, hey, I want the original run data, but this stuff, because I'm going to do statistical analysis, and they'll probably give it to you. So, you know, they're trying to do the right thing, but they're not incredibly sophisticated about it, but at least they've done something along the right line. So I've got to give them some credibility. It's not perfect, but it's a lot of things in the right direction.
Cool. Thank you.
Yeah. How are we doing? Any more questions? I'm happy to continue. It's 11:30 here, but I'm happy to continue.
I guess that's about it.
Okay.
Cool. Thank you again, Dr. Gunther, for your time and such an interesting talk.